So this is my flip video for volumes of solids of revolution, and so let's start by trying to understand what you mean by a solid of revolution. Now, if you look at this diagram, can you see a curve? Actually, it's a parabola, right? Now, if you take this parabola and revolve, so you take this area under the curve, under the x-axis, under the parabola and the x-axis. Okay, so this is this area. Now suppose you just take this area and revolve it around the x-axis, then you see that you will get a like a three-dimensional paraboloid shape. All right. So now our target is from knowledge of this curve, whether we can find the volume of this three-dimensional object, not the area but the volume. Okay. So once again we use the same principle. A big problem is the integral of the small problem approximately, right, roughly speaking. And then, so what's the big problem here? Big problem is to find the area, find the volume of this big object. So the big volume is a big problem. So big volume will be equal to, so we take a little piece here, can you see? So think of this as a kind of a cylindrical kind of a disc, okay, like a disc with a thickness. So we can think of the big volume as the integral of the volume of this small disk. So big volume of revolution is this. So these are called volumes of revolution because you revolve this area and you get this shape. So it's called a volume of revolution. So it's the integral of the small volume of the cylindrical disk. So now if you look at the cylindrical disk, now basically the volume of that cylinder would be the cross-sectional area times the thickness. But because this is along the x-axis and we are looking at a little piece, the thickness is delta x, right? So again this will be what? So the volume of the little problem, or the volume of the little cylindrical disc, will be the area, the cross-sectional area. So remember this one, it's always the cross-sectional area times the dx. Alright, so that's why I said it is the cross-sectional area of the small disk times the thickness. Okay. That is true for anything, even if this was a pyramid or anything, regardless of the shape, it's the cross-sectional area times the delta x. But in our case, the cross-sectional area is a circle. Can you see that? So it's easy to find the area of a circle. So what's the area of this circle? So in our case, it's the area of the circular cross-section times the thickness. Okay. So what is the area of this cross section, the circular of this circle? Well, the area of a circle is pi r squared. R is the radius, but what is r in this case? R, isn't r the radius which comes here? Didn't that r originate from this curve? So it's basically this height, right? R would be this height of the original curve. And what is the height of the curve? That is just y. So the radius, can you everybody see that the radius here is actually y of the original curve? So pi r squared will be what? Pi y squared. Okay. So it's pi y squared. That will be the area of the cross-sectional section, a small disk. That will be pi y squared times thickness of the small disk. So the thickness of the disk is what? Dx, right? Because it's along the x-axis, a little piece, right? So think of this as a little piece. So thickness would be always the delta x or dx that we measure. So what do we get, guys? So the volume of the little cylindrical disk right here is pi y squared, the cross-sectional area, times delta x or dx. So it's pi y squared times dx, right? Okay, so if you integrate that, then if you integrate these little volumes, you get what? The big volume. So the big volume will be the integral of what? Pi y squared times delta x. Now you can use this as long as there is only one curve, right? And as long as the cross-sectional area is circular. But what if it's a pyramid when the cross-sectional area is not circular? Then you got to look at the cross-sectional area as a square, then it will be the area of that square times again delta x, and then again you integrate that. Okay, but for circular ones it's just pi y squared dx. All right, so now in our case the curve y is actually square root x, so all you need to do is to go up here and plug in for y. So we have pi, and then y is square root x squared dx, right, which is pi. Square root x squared will be just what? X. So it's x dx. And what are the limits? So in the problem they tell you to find the limits between 0 and 4. 0 and 4. So you want to find the volume of the only the piece between 0 and 4. So the limits are 0 and 4. Then this is a ridiculously easy integral to do. Integral of x is what? X squared over 2. Pi is there, and you'll put the limits for 0 and 4. So you put the top limit, you get 4 squared, which is 16. 16 over 2 times pi. Minus when you put the bottom limit, you get 0. So 16 over 2 is pi. Pi times 8 is what? 8 pi. So really, what is the volume of the solid of revolution? So volume of the solid of revolution is 8 pi. Okay. All right. So that's the answer. So guys, once again, what do we do? When if we have a curve, say y equals square root x, and if you want to revolve it around if you want to revolve this area bounded by the curve and the x-axis, right? And revolve it around the x-axis, and if you want to get the volume or the resultant volume of solid of revolution, because this is circular, you can easily use the formula integral of what? Pi y squared. So integral of pi y squared, but y squared square root x. Just plug in and integrate in the limit that they want, and you get the answer. Now let's look at another example. So now this time I want to find the volume of solid of revolution obtained by revolved in the part of the circle x squared plus y squared equals 4 in the first quadrant and the x-axis. So x squared plus y squared equals 4 is a circle. So here is a circle, but we are not concerned about the whole circle. We are concerned about, so if you revolve the whole circle, you get a sphere, right? So if you just revolve this part, the first quadrant part, then you get quarter of a sphere. So really we are trying to derive the formula. From that we can easily derive the volume of a sphere that we all know, right? For the thirds pi r cube, right? But how do we know that? So this is a good time for us to actually derive it using calculus. You need calculus to derive that formula for the volume of a sphere. So here is the part that we're concerned about, right? So we want to take this area and revolve it around the x-axis once again, because the cross section is going to be circular, right? So we can use the formula integral pi y squared dx. Okay, so integral pi y squared dx. All right, so what is y here? Y here would be, you need to solve this for y, right? Okay, so if you want to solve this for y, what do we get? So let me solve this for y. Then you will get so really y would be equal to what? Y squared will be equal to 4 minus x squared, right? Okay, and then if you want to take the square root, you get what? Y equals sqrt, sorry, sqrt 4 minus x squared, right? So actually y would be equal to, so solve for y would be equal to 4 minus x squared. That is your curve. Okay, so that is this curve right here. This will be 4 minus x squared square root. Okay, so what you do is you put, for y you just plug in 4 minus x squared square root, and remember there's another square outside, so square root 4 minus x squared and then square dx. But what happens is now we have a square of a square root. So what will happen when you take a square root and then square it? The square root and the square will cancel each other out, and you are left with what? 4 minus x squared. So you have 4 minus x squared, and the limits are from where to where? Well, the limits are from 0 to 2. So let me make it a little larger so that you can see, right? The limits are from 0 to 2, okay, because the limits here are from 0 to 2 also, right, because the radius is 2. Okay, 2 is the radius. Okay, so now if you integrate this one, right, what will happen is the integral is very easy to integrate that, right? The integral of 4 is 4x. The integral of x squared over 3 is x cubed over 3, and that will be equal to, and the limits are 0 to 2, so you plug in that in, you get 8. So when you plug in 2, you get 4 times 2, which is 8, minus when you plug in 2 here, you get 8 over 3, which is 8 over 3. So if you simplify that, so 3 times 8 is 24, 24 minus 8 is 16, so you get 16 over 3. 16 over 3 times pi, so it's 16 over 3 times pi. Now if you look at this answer, if you multiply this by 4, you should get the volume of the sphere. Well, if you multiply this by 4, you get 64 pi over 3, right? Okay, so okay, full volume of the sphere, so you can write full volume of the sphere is what? Multiply by 4, you get what? 64. Which is exactly what you would get if you put that formula that you learned in middle school, 4/3 what? Slash pi, and the radius is 2, so 2 cube. Alright, so because this is a radius 2 circle, so if you really look at that now, you get 8, 2 cube is 8, 8 times pi, and okay, so where did I screw this up? Oh well, I'm sorry, you need to multiply by 2, because you get, if you actually uh, this is actually, when you take this and revolve this, you don't get quarter of a sphere, you actually get half of a sphere, right? My bad. Okay, so you actually get half of a sphere. So if you really want to get a full volume, you need to multiply this by 2, not by 4. So you get 2, so 32, and which is exactly what you will get if you just add it, because 2 to the cube is 8, 8 times pi, 32 over 3. So really it's kind of cool, because you really managed to prove for the first time in your life probably, the equation for the volume of a sphere. Okay, so that's it for this class and for the video. So we'll see you in class tomorrow. We'll work out a lot more problems. Okay.